last time we talked about, so one of the things we talked about last time was series. So we'll continue on that today. So a series is that you have a sequence, you're starting with a sequence, so AN is a sequence. And then you form a new sequence, so you form a new sequence. A new sequence from AN as follows. So the new sequence, let's call that Sn, and S1 is just A1, S2 is A1 plus A2, S3 is A1 plus A2 plus A3, and so on. So this is the first sum of the first n elements. Right? And you typically write Sn. You write Sn as the sum here from, and then in this case I'm starting at 1, but you could start as something else, I equal to 1 to n of ai. And so to say that's the and you write the series, you also write, so this is slight abuse of notation, that you write this infinite sum, as the series. So you think about this as, you think about this thing here, when you write this thing here, you're really thinking about the sequence Sn, right? So you write this for the sequence Sn. And so, so the series here, the series converge. This means that the sequence Sn converges. Right? And so the most, right, so remember that a sequence converges, so we call by the Cauchy convergence theorem, so recall by the Cauchy convergence theorem, that Sn converge if and only if Sn is a Cauchy sequence. Right, and it's a Cauchy sequence just means that if you go sufficiently far out and you're looking at this difference here, then this here is small, provided that m and n are larger than some capital N, where this here is chosen depending on epsilon. Right? That's what it means to be a Cauchy sequence. So like in particular, of course, if you take, so in particular, if you take m to be n plus 1, sorry, let me take m to be n minus 1, doesn't matter. But so if I take it like this, then Sn minus Sm, well, this here is the sum of the first n element, and from that we have to subtract the sum of the first n minus 1 element. So this here, just leave this here, cancel out all of these, and so you're just left with an. So, so this means that if it is converging, right, then in particular, an here has to go to 0 as n goes to infinity, right? Because in fact, this whole difference here, as long as m and n are sufficiently large, have to be as small as you want, right? And so in particular, a special case where this here is the one prior to that, then you see that the an will have to go to 0, right? So again, if you see a series, the first thing, you don't apply any test, the first thing that you check is that this element here goes to 0. Okay, now, what are the most important series? So the most important is the geometric series. And the reason it's the most important is that it can be used to determine, it's easy to determine whether it's converging or not, and it can be used to determine, using the test, whether other series converge. And so the geometric series is that you take a sum. Typically here you start at 0. You don't have to start at 0, but of course the limit, right? The limit, if you take a series, then to say that it's converging means that the sequence Sn converge, and the limit of these here, this here, is also, and that's where there's this abuse of notation, it's denoted by the same thing. So this thing here is playing the role of the sequence, but it's also denoting the limit. Okay, that's just a standard thing. So in this case, I was starting from 1. Okay, so now the geometric series is where you take some number c, and then you multiply it by itself. This is some real number, and you multiply it by itself with itself I times, and where I runs from 0 to infinity, right? And when I is 0, this is meant to be 1. Okay? And the reason why I want to do it here at 0 is that it's probably worth remembering that this here, it's easy to deduce, but it's such a standard fact that this here is converging, so it's converge. So the geometric series converges, provided that the absolute value of c is less than 1, and when it is, this here is the limit. Okay. So then you can ask if c here is equal to is 1, right? So if c is actually equal to 1, not just the absolute value, but if c is actually equal to 1, then it's just 1 times itself a number of times, but that does not go to 0, right? So that's clearly it's diverging, and if it's minus 1 multiply itself by a number of times, then it's just alternate between 1 and minus 1, so it doesn't go to 0. So it's divergent here. And in fact, if as long as c here is bigger or equal to, the absolute value is bigger or equal to 1, because you take this number and multiply it by itself a number of times. If c, the absolute value of c is bigger than 1, then it actually is even blowing up. It becomes larger and larger, right, in absolute value. So it's divergent here and it's convergent. So that was kind of easy, right? And it was easy to determine why we did. There was this little trick with determine what this limit was, right? And this is like a trick that go back, I think, certainly to the ancient Greeks. I mean, this idea, and you can do this with various other things about adding things in different order kind of stuff, or multiplying by something. Okay, so that was the most important, and again, we'll come back to why it is the most important, but it's because it can be used to determine whether other series converge or not. Another classical but that sits inside a family of series, is the harmonic series. So this is an example of a series. It's one series that sits inside a larger family of series. And so the harmonic series is when you take 1 over n and you're summing here, right, like that. Right. This series here, and we saw that last time, is divergent. And in fact, the larger series that is sitting inside sits inside a larger family. And that larger family is where you're summing from 1 to infinity of 1 over n to the alpha, and here alpha is taken to be bigger or equal to 1. And so in the case where alpha is equal to 1, that's a harmonic series. This one's diverge. But if alpha, and so this here is for alpha equal to 1, it's diverged because it's a harmonic series. And when alpha is strictly bigger than 1, well, last time we just saw one example of this when alpha was equal to 2, and we saw that converged. But in fact, you can prove that for any alpha strictly bigger than 1, it does converge. And the typical thing to use there is and we'll talk about that in some later lecture, is what's called the integral test. Okay. Now there is, when you have a series, then most, but not all, most tests, but again, not all, determine really whether the series is what's called absolutely convergent. So what is absolutely convergent? We talked about that last time, but let me remind you. Absolute convergence. So if you take a series here, then here is absolutely convergent, This just means, that the series where you're slapping on absolute value, so this thing here, means that this series here is convergent. And so it's easy to see, so easy to see, and we saw this last time, and it was just from the Cauchy convergence theorem. So it's easy to see that absolute convergence implies convergence, but not the other way around. So Cauchy convergence theorem gives you this implication, why it's not the case that you have the other way around. And that is because what's called the alternating series. So the alternating series, and there's something called the alternating series tests. But let me just explain to you in words why the alternating series converge. So the alternating harmonic series. So if you take the series here, -1 to the n times over n, and you're summing here from 0 to sorry, not to 0, because you're dividing by 0. So from 1 to infinity, this here is called the alternating series. Alternating harmonic series. Right? If you were slapping absolute value sign on it, so this means that an here is minus 1 to the power n over n, right? So if you take the absolute value sign, the absolute value, of an, then this here is just 1, so this is 1 over n. So this here is the corresponding series when you're slapping absolute value. And this is the harmonic series. And this is divergent. Right, that was what we just discussed. Now, why is this series here convergent? We'll probably come back to that in a later lecture in a more general setting, but let me just explain this. And so the idea is that before you're starting summing, so imagine that you have here, before you start your sum, then you're sort of in a neutral position, which is 0, sorry. And then you do the first, thing. You're looking at S1, right? But S1 will bring you down, right? Because S1 is just equal to minus 1 to the power 1, but that's minus 1, so it's minus 1 over n. This is the first element. So that's going to bring you down. Let me just kind of exaggerate the picture and bring you down here to minus 1 over n. Minus 1 over, this is, n is equal to 1, so this is minus 1. This is how the series starts, right? And so the next element is S2, but S2 is minus 1, that was the first element, and then plus, and then minus 1 squared over 2. So this is, and you would be tempted, but it's not, don't add them at this stage, but just looking at it like this. Right? So the next, so this here is S1. Let me just write it down here. This is S1. When you're looking at S2, then you're coming back towards 0, but you don't go as far up as you went down, right? Because it's 1 over 2, right? So this here is S2. And then you see the next one is, if you start here, then you are supposed to, so for S3, it's really S2 plus minus 1 to the power 3 over 3. So this is S2 minus, right, because minus 1 to the power 3 is a negative sign, like that, right? So the next one here, so you're starting here, before you have done any summation, you're starting at 0, you're brought down here, you come up here, and then, but then in S3, you're going down, but you don't go as far down as the previous one. So you're going down here, and so you're really continuing this process, and you see that these intervals get smaller and smaller, and it just goes down, and then it comes up, but it doesn't go up as far up as you were before, and then so on and so forth. And so you can make this more precise. It's quite easy, and this shows you that this series is converging, and in fact, this is like the basis for this alternating series test, and it works as long as you have alternating where the sign of the ANs are alternating and the absolute value goes to 0. Then this here, that's an alternating series test. I'll probably come back to that at some later stage. But this just shows you that if you take a series, then, so the absolute convergence means that if you slap absolute value sign, then that new series also converge. Absolute convergence implies convergence, but not the other way around. Okay, so now the next thing, is that, so the next thing is that if you take a series, suppose you take a series and suppose that you knew that, so suppose you have a series like this, and you knew that an here, all of the an's were non-negative for all n. Then convergence here, convergence just imply, right, so convergence is because the Sn is now the sum here of these guys here, right, that's Sn. And you see that this is, of course, less or equal to, because all of these guys are non-negative, it's less or equal to where you're summing, not just up to n, but one more, right? Because this here is non-negative. And so this here is Sn plus 1. So you see that if the elements are non-negative, then the sequence Sn is, so Sn is monotone, non-decreasing, the sequence. And so to say by the monotone convergence theorem, to say that this sequence Sn is convergent is equivalent to saying that so Sn converge if and only if Sn is bounded from above. Right. Okay, so now when you have a series and you have already checked that an goes to 0, and you are then asked to determine whether the series is converging or not, right? Then there are these number of tests, right? And so there's a bunch of tests. So test for convergence. And so there's a bunch of them. And let me talk about, in this lecture, I'll just talk about the comparison test. And I mentioned them very briefly but last time, but I'll talk a little bit more about them. And then there's the ratio test. And then there's the root test. So I'll talk about those three, but there are other tests. So root test. Okay. Now, okay, so now let's start with the comparison test. And there are like two versions of this. One version is the following, that suppose that you have, so a comparison test. Version 1. And so the first version of the comparison test is the following, that imagine that you have two series here, an, and again we talked about this last time, but let me just say a few more words, that you have this series and you have that series. And I'm assuming here that the an and the bn are non-negative numbers, and in fact I'm assuming that bn is larger or equal to an. Then the comparison test, this version, the simple version of the comparison test is that if this here, if the series based on the bn is convergent, then the series of the an's is also convergent. And so this version of the comparison test is used both in this way, but it's also used sometimes where you know that this series is divergent, and from that you conclude that this one, right? That's just a negation of this statement, right? So, okay, so let's see. So the proof here of that is actually easy. And so why is this the case? Well, the thing is that you know, so that by the Cauchy convergence theorem, we know that to determine whether, all we need to check to determine whether this sequence here is convergent, all we need to figure out is if it is a Cauchy sequence, right? So this means that you want to say that, so suppose you're looking at the series, the sequence, sorry, defined from A. And so this is just where I'm now summing the first n elements in A. And I just want to, right, so I'm using the superscript A just to say, to denote that it's coming from the sequence AN. So if you're looking at this, and so likewise, we look at this thing here. Now, of course, you have that, suppose you're looking at SNA minus SMA. You want to show that this here, is a Cauchy sequence. So you're looking at this difference here, right? But this thing here is just this here difference. I'm assuming that M is less than N, strictly less than N, sorry. This here just means that this difference here is just when you're summing, where you're summing from M plus 1. So this is just the AM plus 1 up to AN. This is just this sum. Right? Yeah?
When we're proving convergence like this now, just like to gain some motivation, like is the reason that we're using Cauchy sequences?
You could either use, at this stage, you could either use Cauchy sequence. That's what I started. You could also have used the monotone convergence theorem. Maybe that was B.
Okay, because I was just going to say, like, back to the definition of convergence that we initially had, where we had, like,
yeah,
the absolute value of, like, A of n minus some.
Yeah, that's right.
Is it just, like,
so if you went all the way back to the definition, right, then you would have to determine what the limit was.
Right, which we don't want.
And we don't want, because we don't know, right? Just because we may know what the limit of B, of the sequence based on B is, but we don't. But this doesn't mean that you can figure out what the limit of the A.
So does that motivate why, like, Cauchy sequences are, like, more useful in general?
Yeah, that's right, exactly, that's right. So the advantage with Cauchy sequence is that you don't have to figure out what the limit is. And it's often, I mean, like in this case, you have no idea. I mean, you know, it's not in terms of anything from the B's, right? And I should, but let me just continue doing it like this. But just now when you ask, I should probably have done it using the monotone convergence theorem. But you can do that as an exercise. But it doesn't matter. I mean, so the difference here is, this is what the difference is. The absolute value signs are really irrelevant because these are all non-negative numbers. So I don't have to have the absolute value sign. So. And now this thing here is, of course, less than, but this here is less than the corresponding B's. And this is like less than the corresponding B here, like that. But this here is exactly Sn, the one based on B, Sm based on B. And this here, as long as N and M are sufficiently large, we can make this as small as we want. So therefore this here was as small as we want. Right. You could also have done it, maybe let's just say like you could also have done it using the monotone convergence, right? Because now, of course, you have that, again, the same sort of thing, say that if you take the Sn based on the A's, so that's A1 up to An, sum of these guys. But this individually is less than the corresponding B's. And this here is just the sequence Sn based on the B's. Right? But these here, if these here converge, this is equivalent to saying that they are bounded. They're less than some C, some real number C. And this here is for all A. For all N, sorry, right? But this means, of course, that those things here are bounded for all N, right? So then, and this here is a monotone, also a monotone sequence, monotone increasing sequence that is now bounded from above, so therefore it converges. So you can do it either of those two ways, but so that's really easy to check. Let's see an example where we are using this test here. And so this could be that you're looking at something like, so here's an example. You're looking at a series that is 2 to the minus n over n, n equal to 1 to infinity. You're being asked, is this series convergent? Okay, so this is like typically how it works. And so, of course, in this case, you should think about that this here is the sequence AN, right? And so you have to find the Bn, right? But in this case, we just say, so we're setting A, so answer, set An equal to 2 to the minus n over 2, and Bn equal to 2 to the minus n. Then you have that An is bigger or equal to 0, is smaller than Bn, and the sequence here based on the Bn, is a convergent geometric series. It's convergent because C here in this case is 1 over 2, right? It's 1 over 2, so it's just, 1 over 2, 1.5 is the same as 2 to the minus 1, right? And so this is convergent. Okay. So this is just so typically, this could be used to that you're given a sequence and you are being asked, is it convergent or not? And so you have to find the series, and you are being asked whether it's convergent or not. And you have to find the comparison series, and then in this case, right, say that this thing here, right, is a convergent, and so therefore the sequence AN that was squeezed between that and 0 was also convergent. Okay, so this was the first version of the comparison test. Here is another more fancy version of comparing, where you're comparing two series. In fact, it's pretty much like that, except for this stuff we talked about. I mean, typically, typically the tests are where you're comparing it with some other series. So here's version 2. So comparison. Version 2. Okay. And so you have again two series, AN, and again it doesn't matter what the sum is, matters where you're starting, but whether or not it converges doesn't matter where you start. So suppose that you have this series and you have this series here. And suppose that you know that the Bn, none of the Bn's are 0. And you know that the An divided by Bn, that this ratio here, as n goes to infinity, converts to some L, and L here is not 0, and it's not infinity, meaning that it really is a limit, like that. So if that's the case, then the series then right, let's right, then let's have these as non-negative numbers. Then the series AN converge if and only if the series BN converge. Okay. And so an example of this, so a typical example like of this, is where you're looking at the series 1 over n squared minus 1. Suppose you're looking at this, and now just to make it so that make sure that it makes sense that you're not dividing by 0, you're looking at this thing here. Suppose that this is the series that you're given. Well, this here is, so you wouldn't use the first comparison, although you could have used the first, but then it would be a little bit more complicated, not super complicated, but a little bit more complicated, because this thing here is, this is, right, so the first thing you observe is that this, of course, goes to 0. This here goes to 0. But the second thing is that it's very close to a series that you know something about. It's very close to this series here. But again, it doesn't matter where I'm starting in order when you're asking whether it's convergent or not. So it's very close to this series. But of course, this thing here is a smaller number. So this is actually bigger than 1 over n squared, right? This here is the convergence series, right? So this does not help you. This is not great for using the first test. You could have done it, but then you could still use the first test, but then you have to be slightly more clever. So instead of that, you can use this second test. And so in the second test, you said AN equal to 1 over n squared minus 1, and you said Bn equal to 1 over n squared. And then you have that AN divided by Bn, but this is just 1 over n squared minus 1 over n squared, 1 over n squared, sorry. And so this here is the same, right, as n squared minus 1, right, like that. And now you can divide by n squared in both numerator and denominator, so you're getting 1 1 minus 1 over n squared. And now you just use the usual algebraic rules for limits. This here converts to 0, so it means that the denominator converts to 1. So this means that this ratio here converts to 1. Right? And so you see that converting the ratio is converging to something that is neither 0 nor infinity. And this means that this series here is convergent. If and only if this here is convergent, you already know that this here is convergent. So we conclude that this is convergent. So that's like how it's typically used. So, right, so now the next test I want to talk about is the ratio test. And so this is, I mean, like the comparison tests are typically like almost the easiest test. But this one here is extremely useful. And so the next two tests, the ratio test, both a ratio test and root test, are based on comparison with the geometric series. And so this is explaining why the geometric series is so crucial. Okay, so what is the ratio test? Well, the ratio test is simply the test that if you're looking at, so if you have a series, you don't have to look at any other series. Like in the comparison test, you had to find another series. But in the ratio test, so this is a ratio test, so you're looking at a series like this. And the ratio test is that you're looking at an plus 1 over an. So you are looking at the ratio between two consecutive elements of the ans. Right? So you're looking at this, and you're looking at the absolute value of this. And you're asking if the limit here as n goes to infinity, suppose that the limit exists, and let's say that the limit is a. So it's asking you if this, it's somehow the test here, this form of the ratio test, it requires that the ratio here has a limit. So the ratio test then say that if a here is if a here is right, sorry, yeah, if a here is less than 1, then the series is, so let me write it like this. So a less than 1, this here means that the series is convergent. Two, if this a here is bigger than 1, this implies that the series is divergent. And 3 is that if this a here is 1, then the test is inconclusive. But so it's important to remember that it is possible that you don't get anything out of the test. Okay, if you are in the unlucky case where this limit is 1. Right? And it is, I should also emphasize that it is crucial to have a limit. Right? So the test here in this form, it's crucial to have a limit. Okay. And we'll talk a little bit, and we'll come back to that, because we'll come back to this. Okay, so now let me try to explain why you have, well, in conclusive, I don't really need to explain anything, right? But why in the case, so proof of case 1. So this means that I have to show, so need to show that if this limit of an plus 1 over an, if this here is less than 1, then the series is convergent. And I'll just sketch the proof, because we're going to do, yeah, I will just sketch the proof. We sort of come back in a way to the proof, because it's very close to the same proof that is used in the case of the root test. So that's what I need. So I have that there exists, so given A0 less than 1, so given A0 with A0 bigger than this A and less than 1. Right, so true. So if you pick A0 that is strictly bigger than A and still less than 1, then we know that there exist n such that if little n is bigger than this capital N, then an plus 1 over an, and really I should have absolute value here on this. Then we have that this thing here is less than, it's less than A0, right? Because if you're very far out, then this here is, this ratio is going to be very close to this, but this is strictly less than that, right? So we have this, right? Okay, so this means that maybe I shouldn't call it A0 because there's too many A's now. Let's call it something else. Let's call it alpha to make it just look much more distinct. Okay, so so this means that, so you see that if, so in other words, if n here is bigger than this capital N, then you have just multiplying over, you have that an plus 1 is less than alpha times an, like that, right? In the ratio test, I should have said that, but obviously you are assuming that these ANs are not 0, so you can divide by them, right? So you have this. If you're far out, you have this, that the next one is a fraction of the previous one, right? But this means, of course, that if you're looking at n is bigger or equal to this capital N, well, you have that A capital N plus 1, right? If you're using this A capital N as little n, then you have that this thing here, this is now this here is now, sorry, if you're using, if you if you first pick n equal to capital N, then what does this inequality tell you? It tells you that a capital N plus 1 is less or equal to alpha a capital N. Now apply this inequality here for n plus capital N plus 1. So then you have that a capital N plus 2 absolute value is less or equal to alpha a n plus 1, like that, right? But you already proven that this thing here, forget about the alpha here, but you've proven this inequality. So filling in that inequality, I have this alpha here, but then I have another alpha that is this, and then like this, right? And so now you can continue this way. So this here is like alpha squared times a capital N. And so now you see that you can continue. So if you're looking at, so if you continue like this, then you see that a capital N plus some little m is less or equal to alpha to the power m times a to the absolute value of an, right? This here, the previous line was just where m was equal to 2, but you really get it for all integers, right? And so this say that at least the tail of this sequence here, the tail of the an sequence, this is just some fixed constant. This here is a convergent geometric series. So the tail is bounded by a convergent geometric series. So you can just apply the first comparison test to prove that the sequence A, that the series AN is actually convergent. Okay, so the ratio test again was to compare it, use the first comparison test where the comparison was the geometric series. Okay. And so, of course, this prove 1, 2 here, but 2 is kind of really the same, because if this alpha here, so to show the second part, again, the third one, to prove it's inconclusive, there's nothing to prove, because it leaves open any possibility. But you want to show that if this limit here, so if this limit, so proof of 2, we're assuming that a here is bigger than 1, but this means that there exists, so if you take alpha, so this time choose alpha such that alpha is bigger than 1, but it's smaller than a. But then you have that for, right, since this ratio is converging for little n bigger than, there exists some capital N, so that if this little n is bigger than a capital N, then you have that an plus 1 over an, that this thing here, if it's far enough out, it's going to converge here, but at least far enough out, it's going to be bigger than alpha, right? Multiplying over again means that an plus 1 is bigger than alpha times an. This here is now bigger than 1. And so in the same way as before, you see that if you're far enough out, then the next element is some multiple, some big number, some at least bigger than 1, times the previous one, right? But this means that they're getting larger and larger as you know, from some fixed stage on and outwards, the ANs are getting larger and larger. So they don't converge to 0 as they were supposed to right? So this is proving true, right? And 3 again, there's nothing to prove because it leaves open both possibilities. Okay.
I have a question about the first proof.
Yeah.
Does that assume that the series is monotone decreasing?
Sorry.
Because we're, like, I guess just looking at it, like, from a high level, we're saying that a of n plus 1 over a of n.
Wait. So you're asking, what are you asking?
So for part 1, when we say that a is less than 1, that implies that it converges.
Yeah.
Is that only going to work for monotone decreasing?
No. So there's no assumption here on whether the sequence is right. I mean, so one implies that the absolute value is going down, as you say, right? Yeah. But it could alternate signs and things like that. Yeah. But it is yeah. And so it's just because you're going to compare it with a convergent geometric series. And in convergent geometric series, the next element is some fixed fraction of the previous one. Yeah. So you're right that in order for the ratio test to give you convergence, then it's going to require that sufficiently far out the absolute value of the AN element is going down. Right? Yep. So the other, and this is like, and this in a way addresses that point you're making there. So the other test that is also based on comparing it with the geometric series, but this does not compare consecutive elements. So it's leaving the possibility that the next element could be larger than the previous. And so this is the root test. But of course, it cannot be that you cannot keep having the next element larger than the previous, right? But you could have, there could be somewhere where, the next one actually went up, but then presumably after that, they're going down at least for a long time, and then maybe there's another one that jumps up, but not very much, etc. Right? And the root test is okay with that, whereas that test wasn't okay with that. So the root test, so you have a series again, like this. And the root test is that you're taking the absolute value of this, and then you're taking the nth root. So this means this is the same as saying an absolute value, if you want to write it like this, 1 over n. Right. So it's dealing with this, and the root test is saying that suppose that when you form this here, that this has a limit. Suppose that this nth root, suppose that this here has a limit, and let's call this limit c. Suppose that you have this. Then it has the same 3 parts here as in the previous. And so this is so there's 3 possibilities where c here is less than 1. Then this implies that the series is convergent. Two, c is bigger than 1, implies that the series is divergent. And again, the case where c here is equal to 1 in conclusion. Test is in conclusion. And again, we're going to compare with the geometric series. So let's see how the proof works. So okay, so now let's prove one. Proof of one. So again, we are in the situation where we have that the nth root of the absolute value here as n goes to infinity is equal to some c, and we're assuming that the c is less than 1. Right? So now I'm again choosing something that is between c and 1, so choose c, so let's call it c0, with c less than c0 less than 1. Okay? And now we know that because we have this limit, we know that they exist. They exist capital N such that if little n is bigger than capital N, then the nth root of this absolute value sign is actually less or equal to C0, right? This is just because C0 was strictly bigger than C, right? So we have that. So now we just take the nth power on both sides. So this implies by taking n power, the nth power we get that a absolute value of an, is less or equal to C0 to the power n, okay? Right, so, but that's already great, right? Because this means that you have compared, at least from a certain stage and outward, you have compared the an with, if you're thinking about that this thing here is like the bn, right? Then it's, you have compared this guys here with this series here based on these, at least from this capital N and outward. And this is a geometric series because it's just some number small, strictly smaller than 1 multiplied by itself n times. So again, by the first comparison test, the an is convergent, right? So and note here that what you're proving is you're actually proving that this series here is convergent, right? Right? Because you're comparing this series here with the geometric series. But this here is just, and this just means, means that the original series here was absolutely convergent. But absolute convergence implies convergence, right? So you are actually proving absolute convergence. Okay. Now let's try to, again, there's these 3 parts to it, but the last one leaves open any possibility, so there's nothing to prove. So let's just prove the second part here, and that's just go similarly. And again, it fails dramatically to be convergent because the an, as we will see, does not actually go to 0. So proof of 2. So we have that this, so we're assuming that this thing here this here converge to some c here, which is now bigger than 1. So this means that there exist, capital N such that if little n is bigger than this capital N, so we have this thing here, and what I should, before I do this, I should choose my, just like before, I should choose my C0, so choose C0 such that C0 is bigger than 1, strictly bigger than 1, but yet is strictly smaller than C. Right? So you choose this, and now using this, we have, because we have that this limit here converts to C, so it converts to something that is strictly above the C0. This means that there exists capital N such that if little n is bigger than capital N, then this, the nth root here is bigger than C0, right? But now again, taking the nth power on both sides, then you have that an is bigger than, strictly bigger than, in fact, C0 to the n power. But you see these guys here, right? C0 is strictly bigger than 1, so this here actually even goes to infinity, right? So this here does not go to 0. Okay. So this prove again that it's divergent. So this prove 2. Okay. Now the next thing we want to talk about is power series. So power series is, so remember that, so the first example of a power series is something we already looked at, more or less. So suppose that you're looking at the series, some number, I call it x now instead of c, to the power n, and n equal to 0 to infinity, right? Yeah. So what we proved, so in the root test here, we proved that the series is absolutely convergent. Here we proved it's divergent, and what we actually proved is we proved that an, in fact, this here an, that is here, allow me to write that it goes to infinity, like this. That they were supposed to go to 0, but we actually, right? If the series was converging, the most elementary thing is, the most basic thing is that the an has to go to 0. Otherwise, it's not going to converge. But in fact, not only do they not go to 0, they actually, in absolute value, goes to infinity. So it's very, very far from being convergent. Right. Okay, so now, so we looked at the geometric series, right? If you think about x as just representing any number, you can look at this series here. This is the geometric series. And we know that it's convergent, so we know that this here is convergent. It's convergent if the absolute value is less than 1, and in that case, this here is, the sum here is just this familiar function. Right? But in general, you may have a sequence, so an, if an, in general, if an is a sequence, then you can form a power series, and the power series is like that, where this is the coefficient. The an is now the coefficient to the x to the power n. Right? So this is, if you will, this is sort of like an infinite polynomial. It's polynomial of infinite degree, right? Because the sum of all these polynomials, right? Okay, and this is called a power series. So this is a power series. So this is a power series. And the question is then, the question, which turned out to be quite subtle, is, so a lot of the basic functions can be represented by power series. This here was one example. Another example is another example of, if you're looking at the exponential function, and we'll come back and discuss this more, but the exponential function has a nice power series representation. And this is the exponential function, the power series representation of the exponential function. And also the sine and cosine. So cosine x, this also have a power series representation. And the power series is -1 to the power n x to the power 2n divided by 2n factorial, where you're summing from 0 to infinity. And sine have a similar one. So sine x has a similar one where you're summing from 0 to infinity, and then it's -1 to the power n x to the power 2n plus 1 over 2n plus 1 factorial. And so, and lots of functions has power series representation, but it's not every function. If I write down a function, then, so in fact, it's easy to write down a function that doesn't have. So if you have, but I'm not going to prove to you that it doesn't. So if I take the function that starts off being dead zero, and now it's becoming interesting. So like this function here, this one does not have a power series, even locally does not have a power series. Okay, and the thing is that power series is an example of something that's called an analytic function, and this here is not an analytic function, so that's why I know that it definitely doesn't have a power series. But anyway, so okay, so now right, so the question is that if you take a power series, so suppose you take a sequence an, and you write it down. Suppose you take a sequence an, and then you write down a power series based on it. Then the first question that comes to mind is, when does this, for which x does this series converge? Right? So for which x does this series converge? So this is like the most basic thing. And let's look at some example. Of course, if you look at so the first example, let me just, that is what we already talked about. Suppose I'm looking at this thing here. Well, this here is, x, if you think about x as being fixed, this is a geometric series. And we already know, so this is for each x, for each fixed x, this is the geometric series. So we already know that this thing here converges, so converge for as long as the absolute value sign, absolute value of x is less than 1, and we also know that it and diverge otherwise, right? Because we've already determined that, right? Okay, now you see, like the next example I want to look at is the one power series that represents but we haven't proven that yet, but we'll talk about that next time, is the exponential function. If I'm looking at this power series here, then I'm interested in for what x does this converge? And so it's natural here to try to apply one of the tests. So you just think about x as being fixed, and you just apply one of the tests. And the natural one is either the root test or the ratio test. Let's do the ratio test. So x is fixed, and I'm not interested in x equal to 0. I'm assuming that x is not equal to 0, because when x is 0, right, this here is just it's only for x to the power 0 is by definition 1, and all the other things all the other terms are 0. Right? So this here it's definitely converging when x is equal to 0. Right? So let's not look at that. And then, because if you don't look at that, you can think about an. You can now think about as the series where bn is x to the power n over n factorial. If you think about this thing here, and you think about the series as now bn, then the ratio test tells you that if you're looking at the ratio of bn plus 1 over bn, so if you're looking at bn plus 1 over bn, take the absolute value of this here. Well, this is just x to the power n plus 1 over n plus 1 factorial, and then you have to divide it by x to the power n over n factorial. Right, if you do that, this here, right, turns up, flips upside down, and you're getting x to the power n plus 1 times n factorial, and then you're getting x to the n times n plus 1 factorial. So this is what it's equal to. And now, of course, here there are x times itself n plus 1 times. The n of those is canceling out with this, right? So this is x. And here you see here the n plus 1 factorial. You can write as n plus 1 and then times n minus 1, etc. But that's just n factorial. So you can write it like that. And so you see that this here canceled that. So you're left with n plus 1. Remember, x is fixed. If x is fixed, as n goes to infinity, this here, for each fixed x, this here just goes to 0. So now you have from the ratio test, if that limit, if it has a limit, it does have a limit. If that limit is strictly less than 1, but it's actually 0, right? So it's definitely falling into under 1, so it's convergent, right? So the ratio test tells you, by the ratio test, this is convergent. Okay? And so we'll finish here. There's a little bit more. I posted already my lecture notes. There's a little bit more, and I'll probably talk about that next time. I'll just start with just talking about the stuff I didn't get to. The stuff I didn't get to was and we touched upon that earlier, is limsup and liminf. And the reason why we're covering it here is that what if the ratio, what if these things, what if the nth root, so you're asking for either the ratio or the nth root of something to have a limit. But what if it doesn't have a limit, right? And so it's dealing with that case, okay? All right, any questions?
That means for all x, right? We're saying, like,
this is for all x, but think about x as being fixed. Right? Think about x, you're just asking for one particular x, but it holds for all x. But don't think about x also as being variable, right? Because x, you think about x as being fixed, and then you let n go to infinity.
Right, and then after you generalize.
Yeah, that's right. And so you have for all x, this makes sense. Right? Then you can ask, how does it vary in x? But that's a different story.